In this lecture, we will dig deep into data center. In the previous lecture, we talked only about computers, just to give you an introduction about different computer components. And I have a question to you before I start the lecture of today. Did you have the chance to watch the video at the end of week 1? There was a video. It was maybe 2 hours video. Did you have the chance to watch all of it without skipping any single minute? Did you have the chance to watch the full video? Who watched the full video, all of it without skipping any part? This video is really interesting, I would say. It is only two hours, which is not a lot of time. Just invest 2 hours of your time. Less than 2 hours, actually. It is 1 hour, 42 minutes. Just to try to invest less than 2 hours of your time to learn more about computer components. You know, knowledge is accumulative. So somehow, if you understand the topic deeply, it will be easy for you to understand the next topic. And sometimes extra material is mainly to give you, I would say, more depth in your knowledge. Oh, no, I mean, not the lecture. Oh, no, Kenneth. I mean, this video. The deeper you understand the topic, the better you understand the next topic. So that's why we have extra material to make sure that you get the depth needed to better understand the topic of this lecture. So every lecture is based on the previous one, and we will build the castle piece by piece, or let's say we will build the knowledge piece by piece. So somehow you need to review the material of every week. After the lecture, maybe you can discuss with your TA, you can try to get deeper knowledge of the subject before we start the next topic, because at the end, it all builds on top of each other. So this is for the previous lecture. Now it is time to start our current lecture. Another thing, some students asked me to share the material I used last week. So during the lecture, I use material that is only for me to make it, maybe to make the subject more visual. I use the material to visualize the concept. The material I use is not really part of the official curriculum. Sometimes I share some links or URLs just because I liked one diagram they have, and because of the copyright, I need to share it from their website. Sharing website does not mean I endorse that website for everything in that URL or in that company or organization. It is only sharing single piece of information to make the subject of our lecture easier. I would say, as a disclaimer, whatever URL I have in these presentations is just for me to show a certain piece of information. It is not an endorsement to this company or that URL or that content. I did not review the full content of the URL. For me, I share the URL only because I want to show you the subjects from different angle, or maybe to add more depth to the subject. With all this out of our way, we are ready to start our lesson for today. Do you have any question about the previous lecture or previous discussion or anything about the course in general before we start the subject of today? Okay, so I will keep an eye always on Slack. I keep an eye on Slack. I don't read the Zoom discussions. I read only Slack live chat during the lecture, and if there is any question, I try to answer it as much as I can, or maybe later the TA can address it. So today our lesson is about data centers. We will discuss data centers in more depth today. We will discuss the overview of data centers. We will not go to the rooms one by one. Today, our discussion is only about the data center as a concept. What are data centers? How they are different from the legacy server rooms? What types of data centers we have? How do we measure the performance of hardware? We will discuss general concepts as a preparation for the coming lectures that will discuss these concepts in more details. Oh yeah, we will talk about A+ maybe at the end of this lecture. Okay, every time we will discuss one subject at the end of the lecture based on the timing. So today we will discuss data centers. What are data centers actually? We will talk about some hardware terminologies. We will talk about the layout of data center. What rooms are there in a data center? We will discuss redundancy, which is an important concept because in data centers, we need to operate 24/7. We need to make sure that we achieve we comply with the requirements, with the SLA requirements or availability requirements. And redundancy is one of the main concepts when it comes to uptime and availability. And then we will talk, we will conclude the session. So first of all, let's talk about data center. What is data center? Now, let's talk about the name. It is data center. So somehow it is all about data. Yeah, as per the name. So somehow it is a location where we have our data stored. But is it enough to have our data stored? Are we only looking for data to be stored? Or we need to run certain applications on data? We need to process data. We need to get insight out of this data. And that's why it is not only about data. We need to have applications that process this data. For the applications to run, they should have three components. They need to have computing or processing or CPU. They need to have storage to store the data. And they need to have network. So computational power, storage, and network, we call them sometimes IT infrastructure. So we have IT infrastructure. We have the applications or the software on top of the IT infrastructure. This includes the operating system, the software. The IT infrastructure needs power and needs maybe also cabling for sure. And then we need to have fire safety, redundancy, other components. So as you can see, although data center is all about data, you need to know about many other components to be able to store data in a reliable way and also to process data. So this is what we will discuss today. We will discuss different components that should exist in a data center and how they are related to the concept of data. So data center is actually a physical building. It is not something virtual. It is something physical and cooling. Yeah, thank you, Gader. So data center is a physical building that should have a lot of rooms and components, and you need to maintain all these components while you are maintaining the data center. Let me show you an example of data center. We will discuss or we will go over this URL multiple times during this course. This is a sample data center for Microsoft, actually. I'm not sure. I think it is in Singapore, maybe. So I would call it the dream data center, maybe, or the ideal data center where we have a lot of buildings and components, renewable energy instead of generators, physical building. You need to have some docking station, or sorry, some so somewhere to load and upload the components. You need to have entrance. You need to have satellite station, and inside this building there will be a lot of rooms. It is not only servers. We have a lot of other spaces that are needed to operate data center. So we will study this URL is for a tour to one of Microsoft data centers. We will have one session. There will be one lecture to go over this location room by room and take a virtual tour into Microsoft, Google, and Amazon sample data centers. This is just to give you an idea about what is a data center. So it is a physical building for sure. So It is somehow a house for computers, network, storage. We always have these three components together. Whenever we mention computers, computers need network, and data should be stored. Typically, we call these components, these three components, as active components of IT infrastructure. On top of these active components, we have the software, the application, the data, the operating system, the software in general. All these run on top of these three components. Typically, data center is used by governments, by other entities to store data. In old days, buildings, or let's say organizations, used to have employees all over the building, and then in the ground floor, usually, they have cabinet with switches and routers and network devices, and they have a small space. We used to call it server room. This is in 90s, in 2000 maybe. They have servers in one room, they call it server room, and this server room typically operate 24/7, but in these days, it was enough to operate it maybe from 9 to 5. If something happened at night, no one cares actually. Nowadays, servers became more and more complicated. They must run 24/7. We have customers connected all the time. We have remote users connected all the time. And that's why the concept of server room expanded to what we call as data center, where we have data center as a physical building only for servers, only for data. And somehow we looked for ways to share data centers. Data centers are expensive. We need to operate them 24/7, which means for organization to have a proper server room or proper data hosting, they need to have teams operating 24/7, which is expensive. And that's why they started to look for ways to share the cost. Why would any company want to own its own space? How about if we share it with others? So every company has its own servers, but they share the same infrastructure. They share the same cooling infrastructure, the same power redundancy. They share the same maybe fire safety. They share some of the components to make the cost of hosting data cheaper. And there are different concepts that evolved over years, starting from colo, which we will discuss later in this lecture, to the concept of cloud computing. So let's go over these steps or these stations one by one to understand the journey of data centers from old server rooms to the current cloud computing. So imagine the information you have or you share over the internet, over Instagram, TikTok. All these informations are shared or stored somewhere in servers. You have no idea where are these servers, and that's why we call it cloud. Cloud means the information is stored in certain data center, but we have no idea what is that data center. And that's why we just say cloud. Cloud means, so cloud means the information is stored somewhere in the internet. We don't care, or maybe we don't know where the information is stored actually. And that's why we just say cloud. Cloud is a collection of a lot of data centers interconnected by high speeds. And these data centers are owned by different entities. Because we have no idea about them, we consider them as a cloud. So a lot of data centers interconnected. For us, when we look from the outside, we consider them just as a cloud. So the cloud is actually a hardware. It is a collection of many data centers interconnected, and we call them the cloud. In this course, we will dig more. We will understand the components of these data centers. We will discuss how they are connected somehow to a certain extent, not deeply actually. And we will focus on single unit, which is data center. The unit of the cloud, the building unit of the cloud is data center or data center. I know that some people say data, some people say data. In Canadian accent, we typically say data, but it is data also. So data center is the building unit of the cloud. And this is the subject of our lecture and our course. Let's talk about how data center work, and let's watch this video. It is a short video, and it will explain a lot of subjects. I think I need to share with sound. Let me stop sharing and share with sound again, because sharing with sound will make the sound much clearer than sharing without sound. Okay, I shared with sound, and I hope I'm sharing the right screen again. Yeah, it is, I believe. Can you hear the sound when I run it? Okay, great. So let me start again. It is only 2 video. Let's watch it together, and then we will discuss it.
A Google search, a YouTube video, a connected Nest device, and hundreds of Google Cloud services all give you a response in a fraction of a second. But what really happens when you click search, send a request, or say, "Okay, Google"? Well, your message travels over the public internet.
So all these are data centers for Google. When you do search in Google, do you have any idea which one of these data centers provided you with the information? Or maybe when you store a file in Google Cloud or Google Drive, do you have any idea which one of these data centers provided you with the service? No, you have no idea. And that's why they just call it the cloud. But at the end, it is a collection of data centers, physical data centers, just distributed all over the globe. And you, as data center technician, you will work in one of these, and you will be responsible on operating one of these data centers and to make sure it is available 24/7, 99.9999% of the time. So this will be your responsibility in the future to run one of these data centers that together form what we call as a cloud.
And into Google's global fiber network. Millions of these requests or packets of data travel through miles of cable over land and undersea, converging at—
Yeah, I know it is Google, and you will be in Amazon one day, AWS, but I mean the concept, whether Google or AWS.
One of the many data centers we operate all over the world. But besides delivering quick results back to you, what exactly is a data center? A data center is a building with powerful computers used to run a company's services. It's where information is processed and made available. Data is stored, managed, and disseminated across these computers. And network infrastructure is installed to support web apps, databases, virtual machines, and more. Often, organizations start with their own modest buildings made up of a few server racks, which requires maintaining these systems, paying for cooling, and handling increasing demand.
So for companies, when they own their own server room or data center, it is costly. I have seen many situations where companies fail to deliver the required SLA, service level agreement, when they have their servers on-prem. On-prem means inside their physical location. So when they have the servers inside their physical location, they struggle in maintaining these servers 24/7, in patching them, and maybe providing redundant power, redundant cooling, a lot of factors they need to consider, which are not easy to provide for normal organization. And that's why they started to offload this burden to third-party companies like Google, AWS, or Microsoft, or many other solutions we will discuss later in this lecture.
So many companies look to a cloud services provider like Google Cloud. These providers' data centers have evolved into large campuses of multiple buildings. Hyperscale data centers, made up of tens of thousands of servers, process big data, support cloud computing, and serve billions of users for services like Chrome, Maps, Gmail, Search, and Google Cloud. In the cloud world, companies and users can benefit from this scale because of a special thing called multi-tenancy.
So this is one of the key concepts in the cloud. We have one building serving many. So instead of you own your own building, your own data center, and you pay for all the facilities, all the redundancy, all the high availability, all the staffing for that location because it is single tenant, instead of having owning your own data center and spend a lot of money in maintaining it. How about if we share these resources? How about if we have data center that is shared by multiple organizations, and we call it maybe a cloud because it is maintained by third party and we don't care about the exact location. So there are multiple concepts of multi-tenant or sharing the data center. We will discuss them in more details, but this is the concept of reducing the cost. We want to reduce the cost of operating data centers, and that's why we use the concept of multi-tenant to share the cost between multiple entities and make it more feasible.
This means customers can share the resources of each server in a data center, like tenants sharing common resources of an apartment building. Each tenant's cloud systems are isolated and invisible to other tenants. This means higher compute processing and storage, a more efficient use of data center resources, and a much lower cost than if you manage your own servers. Google Cloud customers can even deploy resources in regions across the world, which are enterprise data center locations with 3 or more zones. Zones are deployment areas.
So we will talk about redundancy later in this lecture. Redundancy means we have a replica of resources. So if one of these replicas failed, the data center is still operating. So Google, Amazon, Microsoft, when they operate data centers, they don't have it as one building. They have multiple copies within single region. We call them zones. So let's say in New York region, typically they don't have it inside the city, maybe around the city. If they have one, if they want to provide service in New York, they need to have 3 copies of data center at least. So if one data center failed, the other 2 are still operating. They call them zones. We will talk about redundancy more later today, but this is the main idea. We want to make sure the service is available all the time, almost, and that's why we need to have some sort of replicas or maybe redundant data centers just in case of failure to provide the service to customers.
That map to clusters of machines with distinct physical infrastructure. Companies can deploy workloads across multiple zones to help protect against unexpected failures, something you can't always get with a single private data center. It takes the right mix of energy, cooling, and people to keep a data center up and running. But it's a technical feat Google's managed to pull off to optimize for efficiency, scale, and cost. More on that next time on.
So the same concept applies to Amazon.
I'm sorry to interrupt, but you're not sharing your screen. I think it got disconnected.
Oh, really? Oh, I wasn't sharing all the time?
No, you just now.
No, we see it.
Oh, really? Okay, no worries then. Sorry.
I thought something wrong with my internet, but yeah, it is good.
Yeah.
False positive, they call it in security. Oh, thank you. No worries. Thank you for informing me. Just yeah. So now the same concept applies to Amazon, to Microsoft, to Google, to Oracle, to any of these cloud service providers. We call them CSPs, cloud service providers, like Microsoft, like Amazon Web Service, like Microsoft Azure, like Google Cloud Platform. So all these are cloud service providers, and this is what we have here. So there are different levels of data center. The first level is on-prem, which was legacy, the typical way. In old days, companies, they have their own data centers in the same building. They have server room or a small data center in the same building, which was not easy to maintain and operate. It was costly somehow. Later, they thought about sharing resources, and a new concept emerged. It was called colo. They call it colo. Instead of co-located data centers, they abbreviate it as colo, which means companies that build large data centers and then they divide it into physical spaces and they rent out these spaces to different organizations. So let's say your organization wants to own their own data center, their own space. Instead of owning or installing the servers in their own data center, they rent a physical space in a co-location data center. They still have physical, I would say, ownership. They still have their own servers, physical servers that are owned by them, controlled by them, but they relocate them physically into one large data center where the company who provide the service is responsible on maintaining the power supplies, redundant power supply, maintaining the cooling, maintaining the physical security, and maintaining even the internet, provide a lot of internet bandwidth, a lot of maybe WAN links and other services. So this was the concept of co-location. Now let's stop for a minute and think about it. If you are an employee in this co-location and you don't maintain the power redundancy in a proper way, and power disconnects, for example, the whole data center is down. So instead of having 99.999% of availability as you promised your customers, your availability reduced or went maybe to 99.9% only. Do you think customers will be happy? So SLA is service level agreement. If you are unable to maintain the SLA, do you think customers will be happy? No. And are you gonna lose business? For sure. And maybe you will pay penalty to these organizations. So availability in data center is critical. You as data center technician, you have high responsibility, because if you didn't maintain the equipment in a proper way and the SLA or the availability of data center went below the approved or accepted or required level, then the data center will lose business and your company will lose and close maybe because of bad actions of data center technicians. So that's why it is important for you to know the concept of redundancy, availability, and this is the objective of this course, to give you the knowledge needed to understand how to achieve these levels and how to measure them. Now, the other thing, that this was co-location, which means you know exactly the physical location of your building or of your servers. There was a concept of co-location, they call it caged. Let me show you some photos. So this is an example of co-location. So inside co-location, they have cages for every company. So you as an organization, you go to co-location provider and you rent one of these cages. You have the lock for that cage. You control the access, the physical access to that cage. You install your servers inside. You own that physical space. You get the internet from the data center operator. You get the WAN link, you get the power, you get the cooling, everything as per the SLA from the data center operator, but you have your own physical space. You know exactly where your servers are located. You select the servers, you install the applications, you maintain the servers, but the space, the services, the power, the cooling, all provided by the data center operator. So this is the concept of co-location. On the other side, cloud is a bit different. Cloud data center is somehow more virtual, maybe. I would say you have no idea where are your servers or applications or data is exactly located. You just agree with Google or Microsoft, you agree on the region. You don't need to know the physical location of their data centers. All what you need to know is that your data is hosted maybe in US West or US East, and everything is handled by the cloud data center. You have less headache, you have more peace of mind maybe. They manage everything for you. You don't worry about anything. You have less responsibility maybe. They have more responsibility here. and somehow it is maybe more dynamic. You can easily scale out, scale in at any time without the need of any physical deployment. So there are limited number of cloud service providers, Google, Microsoft, Amazon, Oracle, and some others maybe. They are different than colocation because you don't know the physical location of your equipment. You don't own your equipment. You don't rent a space. It is all about having an agreement, and everything is managed by the other company. Somehow, there are levels of responsibilities. We will talk about them later. For now, it is just the concept of cloud. So do you understand the difference between on-prem servers or on-prem data center, colocation, and cloud? Oh, good question, Kenneth. So, Kenneth, about what happens if server fails. As we discussed before, these companies, they have replicas of all servers. They have ways to deal with failures. So they have no single point of failure. So if one of the hard disks failed, they already have replicas in other locations, and every hard disk or SSD have some replicas. They use concepts like RAID or other redundancy concepts that we'll discuss later. So if one hard disk fails, the data can be recovered from backups, and you don't feel it. It happens within maybe seconds or milliseconds or maybe less. And also, they have some sort of they distribute the data. They distribute the data in a way to make sure it is always available, even if one rack fails. They have some sort of they call it failure domains, update domains. So when they update the servers, they make sure your data is somehow your data is served by another server that is not updated. If your data is served by two different servers, they don't upgrade both of them at the same time. They upgrade one at a time. So they have a lot of rules to make sure that your service is available at any time, even if one hard disk failed, even if one server failed, even if one rack failed, even if one data center failed, because they have another zones within the same region. So they have different ways to deal with this. Latency is a challenge. We will talk about it maybe later, but for now, let's take it one piece at a time. So what do data centers do? What are the main functions? Now, as I keep saying, they are mainly for data. They store the information, but it is not only about data only. The data should be processed and should maybe there should be some applications to get insights, to provide services using that data. There should be computing power, there should be networking capabilities, and for sure there should be storage to store the data. We will talk about these components. So for data to be available and to be useful, we need to have a lot of other components. Data centers are used by government, by educational institutions, by telecom companies, by enterprise companies, by business organizations, retailers, social network. All these are based on data and data centers. Now, everything is moving more and more to digitalized. We have what we call as digital transformation. Everything becomes digital. And when we say digital, means data and means data center. Another component is the storage. We need to store data. And for that storage to work, it is not only about hard disk or about maybe storage media. There should be some computers to run and to provide some interface to deal with these storage medias. There should be some programs to store the data, to restore the data, to have a backup, to provide some sort of redundancy, to provide some monitoring information about storage media. And there should be a process: when to store the data, for how long to archive it. Do you want to store the data to infinity, to have it stored to infinity, to unknown time? Do you want to have all data stored at the same level all the time? Or maybe you want to have some sort of archiving after a certain number of days. Maybe some of the data will be available in SSD because it is more accessible. We call it hot data maybe. And all data maybe can be stored in hard disks, cheap hard disks maybe, to be available for archive for maybe 5 years. And then we dispose the data, we delete it in an compliant way. So all this is a process. There should be a process to deal with the information. So we cannot just dump data and expect it to work. There should be a lot of rules, a lot of planning, how to collect the data, how to access it, how to secure it, for how long to keep it, and even how to delete it. Deleting data is also a critical component of compliance. You cannot just delete the data and expect it to be permanently deleted. There are certain procedures to make sure that the data cannot be recovered by any means. So somehow deleting data from the hard disk is not enough, because the magnetic field is still keeping the data, still storing the data. There are certain ways to make sure that we permanently erase the data and it is not recoverable by any mean. So all these are factors you need to consider when you discuss your data policy. The good thing with the cloud is that somehow you throw it on them, but on the other side, you have less control. You need to trust them. You need to rely on them to comply with the requirements, with the regulations, and somehow they will be in charge of this more than you somehow. So mainly when you deal with critical sectors, or maybe sensitive sectors like finance or medicine, there are regulations. The governments don't leave it to you to control the data, because if you work in a bank, data is money, and this is financial information that affects a lot of people. If you work in medicine, if you work in a hospital, the health records of people is very confidential. So the governments don't leave it for you to control this. They set what we call as regulations. If you work in a IT department in a hospital, you must comply with certain regulations that control who can access the medical records, how medical records should be encrypted, what information can be shared with different groups. Do you know what is the name of regulation that manages medical records in the US? Does anyone know the name of regulation that manages or controls HIPAA? Yeah, thank you. So HIPAA is the regulation in the US to control how to store and access and encrypt and maintain the confidentiality of medical records for the public. So it is not up to you. You need to follow these regulations. There are some regulations for finance. They call them, I think, SOX. Yeah, there are different names for regulations. So you need to know the regulations that control your sector or your area, and you must comply with these regulations. Otherwise, you might be subject to penalties, and people may sue you in the court. So you need to be careful when you deal with data. So when it comes to data storage, you need to know the components. You need to understand what components, what hardware is needed for this storage, SSD, hard drive, or others. You need to know the organization. You need to understand what are the rules to store the data, and what are the softwares and tools used for that. And also you need to know the industry regulations, mainly if you work on finance, medicine, or even if you store customer information, you need to know the regulations. So this is the storage. So we discussed the hardware. We said that application, computer, network capabilities, storage is another component in data center. Applications. So data, raw data, is not useful by itself. It is not enough just to have tables and tables and tables of data. We need to have applications to give us insights, to give us maybe to process the data and provide us with more meaningful information out of this data. And this is the function of applications. Applications are typically designed to provide us with more business insights and business intelligence out of the raw data that we have. Typically, these applications can control maybe databases, can store and organize data in databases. They can provide analytics. They analyze the data, they decipher the data, they find patterns in data, they find trends. They give us, for example, if you have information like our sales over years, where like this, we have the numbers. Our sales in 2000 was 1 million, 2001 it is 1.1, 2002 1.3, 1.5, 1.7. Let's say these are just numbers, raw data. They don't give you any business intelligence or insight. Applications would maybe convert this into drawings for you to know the trend over time. So you know that your sales are increasing. Maybe it gives you information about the productivity of employees. If you have the number of employees, for every employee, you have number of working hours and achievement they did. And you want to know which one of your employees are more productive. So you can make a drawing and it can give you a bar chart of productivity for different employees. And this way you know that this employee is more productive than this employee. So applications are the tools we use to get insight or to get more intelligence from our raw data. And typically they are they store the data in databases. They analyze them to get some insights. And also the applications should implement some security measures. Maybe they encrypt the data, maybe they mask the data, maybe they anonymize the data to make sure our informations are protected. So this is something to consider. So data center is much more than just data. It should have a lot of components in addition to data. Now, one of the concepts that are related to storing data is the concept of big data. Big data is some sort of concept. It is not, I would say, it is not well defined. How much data is big data? Big data means when we started collecting more and more data, maybe from 1980s to 2000, 2010, so somehow they discovered that we are collecting every year, we collect much, much more data than what we collected in the previous history. They say we currently produce, every year we produce more data than what was produced in history. I think if every 1 or 2 years we produce data that is more than what was produced in human history since the start of writing. So somehow we are producing more and more data every year, and it is exponential. So every year we produce much more data than the previous year, and this goes exponential. At certain point, they said we have big data, we have a lot of data, to the point it became difficult for us to digest it, to understand it, and they starting developing a new trends or a new concepts or a new branches of science that are mainly to process, analyze, and understand this big data. So when you hear someone says, I am a data scientist, do you know what is data scientist? What they do? Data scientists, sorry for the misspelling. So data scientists are mainly people who process this huge amount of data They try to find trends of this data. They try to use machine learning to predict the future. They use machine learning and AI tools to maybe classify data. So this is a lot of new branches of technology and science emerged after the concept of big data. The big data means we have collected much more data than what we can process using the old tools. And we reached a point where the new tools are needed and required to process this large or this vast amount of data. So the concept started maybe also many years ago, maybe 10 to 15 years ago. And they started using more machine learning, more business intelligence, more data science, more statistical tools to discover new trends and new patterns out of this data. So they started having, or they started using concepts like data economy, data-driven decision-making. Everyone says, I want to depend on data. Data is considered as the ground truth. It is considered as the ultimate fact for any decision-making. And with the vast amount of data we have, a lot of new trends emerged, all about using data to make more informative decisions, to make more accurate predictions, and they start adding the word data to any process. They say data-driven organization, data-driven decision-making, data-driven business decision. So everything is data driven. And all this started by the concept of big data and the digital transformation, where we started to convert everything into digital. We are able to store it. We are able to process it using computers. And all this revolution we have nowadays is based on data. So big data is the concept of dealing with vast amount of data. How can we collect this large amount of data? How can we process this large amount of data? It has a lot of missing data, missing components, missing fields. How can we clean this data to make it more accurate and more consumable by our tools? And at the end, how can we consume this data? How can we analyze it to get more insight, business-related intelligence, and to support our decision-making procedures? So this is big data, and you will hear this term a lot in conferences and in seminars. Splunk is for security, for handling security data and security logs. Splunk is one of the best. But when it comes to business intelligence, when it comes to IoT analytics, there are other tools that are mainly dedicated or mainly focused on certain area of big data. Yeah, everything connected to the internet generates data, and this data is used. Now this lecture is recorded, and this is also adding to big data. All the discussions we have in Slack can be used in big data, but I know for privacy sometimes not everything can be shared for analysis. But I would say anything you type in the chat, anything you type in your device, this adds to the accumulative knowledge we have as a humanity, and can be used to generate more content, can be used to train the computers to be more accurate, more useful maybe. Now, yeah, we need to move faster. Okay. So with all this data we have, we reach to the point where humans are unable to visualize it, unable to get insight, unable to discover the patterns and trends. And they started to use machines to get that information. So they started to feed information to machines. The machines will learn out of this data, and then machine can predict the future, can classify new information. So the concept of machine learning is we have a model. We call it machine learning model, ML model, which is some sort of mathematical information, mathematical connection between a lot of mathematical, let's call it formulas, equations interconnected. We feed it with a large amount of information, data, that is well organized, in a way that somehow can be used or can be digested by the machine. The machine will learn from this data, will build certain relationship between different components in the model, and will be able to get to provide accurate output. Then we use part of the information to train the model. Then once the model is trained, we take it, we feed it with a new information that it has never seen before. And guess what? The model will be able to predict the output. So for example, if you want to know which one of the students will pass, which one will fail, we give the model information about the past. The model learn it, understand the profile of every student, and then you give the machine the profile of a new student. The machine can predict whether the student will pass or fail. The bank can use it, for example, to predict whether the customer will default or will pay the loan. They give the machine information about previous customers with their profiles, with their income, house, number of children, all the details, and then they feed the model with information about a new customer. The model say this customer will default or will pay. So the machine will learn about all information you share over the internet, typically will be fed to the machine to learn about you, and then the machine can predict things about you, can give some insight, can predict what product you will buy and what services you will use in the future. So this is the concept of machine learning and how big data helps in machine learning and in advancing technology in a positive way. Now, there's always some negative ways of doing everything. Every technology has its own positive and its own negative. But anyway, so we will in this course we'll navigate the digital frontier and we'll talk more about these concepts. Now, a question: which of the following best describe co-located data centers? A, B, C, or D? Yeah, thank you. All correct. So it is shared facility leased by multiple companies, which is correct. So this was the first part of this lecture, which is data center. And now we need to understand how to measure the performance of data center. If we have a data center, how would we say this data center is better than the other one? What are the metrics? What are the performance KPIs, key performance indicators, that we can use to compare different data centers or maybe compare different components within data center? So we will talk about 4 metrics or 4 terms: availability, reliability, durability, and resilience. All of them are somehow related, but they have very, I would say, tiny difference between them. So first of all, what is availability? Availability is the ability of a system or component to perform its intended function when needed. So for example, if you try to, let's say you have a service and this service mainly used to give you employee name, maybe employee information. So you enter the employee number, then the system will give you employee information. If you type the employee number and then you get no service, then the service is not available. Availability is one of the key terms or key metrics to qualify or to compare different data centers. How can we improve availability? Typically by having a replica of the system. So if this system down, if your request goes to this system and this system is down, there should be a replica of the system to provide you service when this one is down. So this replica, we call it redundancy. Redundant, we add redundant component, which is not used unless the main component is down. So availability typically improved by redundancy. We will talk about redundancy later in this lecture. The other component is reliability. The hardware and the system you use in data center should be reliable. Somehow you can say, don't use cheap components that are not designed for reliable data center. Don't use home hard disk, or let's say home grade or consumer grade hard disk in data center. You should use something more reliable. You use the component and the hardware and the software that you can rely on. Reliability means the system performs the intended function without failure. So if you have a hard disk and you want to get a file from this hard disk, you expect the hard disk to give you always the same file. If there are certain parts of the hard disk that are defective or maybe infected or whatever, it will give you different file with maybe missing parts maybe. So this means this hard disk is not reliable because it doesn't give the same file all the time. Somehow it has some corrupted sectors and it doesn't provide the same information. Now, do you think SSD is more reliable or hard disk drives? If you remember the lecture of yesterday or last week, sorry, which one of these two is more reliable? SSD. Why is that? Which one of these has mechanical components? Which one of these has mechanical components? The hard disk. So mechanical components are not that reliable. They are subject of failure maybe. They can maybe get broken easily. On the other side, SSDs are more electronic. They have more precise components. They provide the same results every time. So for example, SSDs are more reliable because they give the exact same result every time. They don't depend on mechanical components that are subject to failure. So this is somehow some sort of reliability. The other factor is durability. Durability means the system will withstand wear and tear over time. So for example, in your data center, you have generators. Why do we need generators? Typically, why do we need generators? Backup power, thank you. Do you think generators should be indoor or outdoor? Do you think generators should be inside data center or outside? They are typically outside. They may have their own compartment. They may have their own maybe shelter or whatever outside, but they are outside the building. If you have normal or if you have ruggedized generator, or maybe if you have indoor generators, which one of them will be able to withstand the snow and the bad weather for longer time? Do you think the one which is ruggedized and hardened, or the one that is designed for indoor deployments, maybe for maybe normal home users? Yeah, the one that is ruggedized will be more durable. So when you design your data center, you need to consider durability. You need to make sure the components you select can withstand the environment, even indoor or outdoor. They should be more durable. They don't fail by any maybe weather conditions. The fourth component is resilience. What is resilience? Resilience means if you have a system and the system has multiple components, let's say, resiliency means if one of these components fail, the system will be able to recover quickly. So it is about how fast the system can recover in case of failure. So maybe you have redundancy, but somehow you don't have a proper software or proper protocol or proper design. And in case of failure, it takes maybe 1 minute for the system to recover. So you have redundancy, but the system takes long time to recover in case of redundancy, which means the system has bad resiliency. Now, resiliency somehow is about the logic that connect these redundant components in a way that makes sure in case of failure, the other part will take the service or bring the service up immediately. So it is about the time, how quick the system can recover in case of failure. So resilience, yeah, now consumer level components are not reliable. Consumer grade components are not even redundant. Sometimes they don't have redundant power supply. They don't have redundant CPU. So they have bad availability. They have bad durability. They cannot withstand the harsh environment outside, or even they cannot withstand the variation of temperature within data center. Maybe they are not resilient. Actually, consumer grade components don't achieve any of these. They are bad in all aspects. So yeah, so I like it, Victor, but actually they lack everything, not only resiliency. Now, to make the concept clearer, maybe we need to compare components. We need to compare components. So let's compare availability with reliability. The two concepts are similar, actually, but there is a fine difference between them. So availability is how often the service is able to respond to requests. Typically, we measure availability by percentage. So is it available 99.9, which is 3 nines, or is it available 99.999, which means 5 nines? So how often the service is able to respond to requests? This is called availability. But maybe it responds with wrong information. Maybe the hard disk is responding and provide you with the information, but the information is wrong or corrupted because the hard disk of bad quality. So sometimes the system is available but not reliable, because reliability means the system is responding as intended. It provides you with the information needed, the accurate information, then it is reliable. So reliable system is the system that can provide the required information. Can it be reliable but not available? Maybe. Maybe the storage media is reliable, it has the information needed, but maybe the power supply is down or the network is down. So reliability is about how reliable is the hardware. Availability is about responding to the request. In most cases, reliable systems are also available because typically they should have redundant power supply, redundant CPU, redundancy at all levels. Typically, these two, the company or the product that is reliable in most cases will have also the components in a redundant way and will be available in most of the cases. But this is just a comparison between the two concepts. And also, in similar way, if you want to discuss durability versus resilience. So this is availability. As we said, it is measured in percentage. And typically, it is number of nines. In data centers, typically, we are looking for 5 nines. In many cases, it depends on what level you want to achieve. Some data centers are trying to achieve 5 nines, which is 99.9999% of uptime. Some data centers are looking for 99.9. They believe it is enough. And this means 99.9% availability. This means in the year, they can have only 8.76 hours of downtime. So who decides how many nines? We will talk about it. There are certain certifications. So some data centers are certified to be tier 1, tier 2, tier 3, tier 4. And the more or the better tier you have, the more trusted you will be by customers. So some data centers are looking for the highest certification. They want to achieve the highest availability because this helps them getting more business, and they get better customer trust by being certified as T4. Other data centers are good with 3 nines because they believe the cost of becoming 5 nines is high. We are not targeting these high profile customers. Maybe we are targeting only 99.9 customers. So it depends. We will discuss this more in the coming lectures. When it comes to reliability, it is measured by a concept called mean time between failures. So mean time between failures means, for example, if you have a hard disk or SSD, or let's say if you have a server, they do some calculation to decide how many years it will take the server to fail. So if mean time between failures is 3 years, for example, then they expect the server to fail every 3 years. If it is 10 years, then they expect the server to fail every 10 years. Which one is better, 3 years or 10 years? When it comes to reliability, if we measure the mean time between failures, which one is better, 3 years or 10 years? 10 years for sure. Now, they don't actually run it for 10 years to measure the number. Typically, they do some analysis on the components. Every component has its own measurement of quality, and somehow they can say this server is expected to fail every 10 years, 20 years, some of them maybe 100 years. Does it mean that this server will not fail for the coming 20 years? No, this is the mean time. This is the average. But maybe you are the non-lucky guy and your server will fail after 1 year, but your neighbor will have the same server failing after 30 years. So when they say mean time between failures, this is they take the average of all servers of this model, but for you, it depends on your environment, and sometimes it happens that the server, in your case, failed after 1 year. Yeah, others, maybe they will get it 30 years, and the average is 15 years. So we measure typically mean time between failure and mean time to failure, which is used to measure the first failure and the second failure. Now, before we stop, let's continue this, then we'll have the break. On the other side, durability and resilience. Durability means the equipment will be durable and will withstand the environment. It can be durable but not resilient. Resilient is about how fast it can recover after failure. Durability is about how long it can operate under certain circumstances. So these concepts, you need to maybe review the definitions multiple times to make sure you understand them very well. In the future lectures, we will use them in calculating the availability of the data center and to measure and compare different components in data center. So what strategies we can use? Think about it during the break, and after the break, we will discuss it together within the coming lesson. So now, are we gonna have 10 or 15 minutes? Maybe let's have 15 minutes a break. Last time we gave 10 minutes, and some people believe it is short. Let's have 15 minutes break this time. Is this okay, Megan and Raya?
Yeah, that works. 15 minutes sounds great.
Okay, everyone, let's have 15 minutes break. During the break, think about this. How can we improve the reliability, the durability, the availability, and resilience of the system? Everyone, give me 1 minute. Let me share my screen. To make sure I'm sharing the right screen. Okay. So make sure, do you see how to improve performance? Do you see how to improve performance in the screen I shared? And let me show my cam. Wait a minute, what's going with my cam? Give me 1 minute, let me fix this. Yeah, good. Okay, small technical glitch, and it is fixed now. Okay. Yeah, can you hear my voice? See my cam? Can you see my screen? Great. Now, how can we improve performance? This is the main question we had before the break, and now it is time to answer this question. How can we improve the performance? Now, let's think about it. First of all, we want to improve availability. We want our application to be available all the time, 99.9999. We have different ways to achieve this. We can spread the application across different locations, maybe. So we want our application to be available all the time. We can spread it into maybe 2 different servers, maybe. So in case of one server fail, the other server will be available. But what if the full rack is down? Maybe better to have the servers in 2 different racks. The rack is this cabinet where we have the servers mounted. We call it rack or cabinet. So how about if the whole data center is down, maybe we can have the servers in 2 different locations, one in New York, maybe one in New Jersey, maybe. So we need to have replica of the system in different locations. Maybe we can have load balancing, which means when the requests come from the user, the requests are distributed between different servers in different locations. And if one of these servers fail, the request goes to another location. So these are some of the ideas that we can use to improve availability. How about reliability? How can we improve reliability? Maybe to improve reliability, maybe we can select proper hardware, maybe. This is one thing to improve reliability. Maybe we have test procedure to simulate the scenarios and make sure that the system produces the same result every time. And we make sure our design is built in a way to produce the same result every time. How to improve durability? Maybe we need to make sure that, again, we need to select the proper hardware. And also, maybe we have different backups, multiple backups. In case of failure, we can recover the system from these backups. Somehow, as you can see, all the comments are about having more replicas, more redundancy, selecting proper hardware, proper systems. Somehow, these things are interrelated. If you improve one of them, you will improve the others. And that's why we have one concept called fault tolerance. That means the summation of these components together. Resilience can be achieved by having the software and the tools that can recover the system when failure happens. In many cases, the same results or the same suggestions are repeated more and more. And that's why we will have a concept called fault tolerance that reflect all of them. So what is fault tolerance and what we can do to achieve better fault tolerance? So the concept we discussed, availability, durability, reliability, resilience, all of them, they feed the concept of fault tolerance. Fault tolerance means the ability of a system to continue operating even in case of failure. If our system is available, durable, resilient, and reliable, then we have better fault tolerance, and the system we can operate even in case of failure. Even if one component failed, it will continue working. What do you mean by component? So when we say a system means, in many cases, systems means compute plus storage plus network plus software plus data. So this is somehow called system. System is multiple components. Instead of us saying the server is not enough, because if the server is working but the network is down, then the system is down. If the computer and the network are working but the storage is faulty, the system is down. If all of them are working, but the software has bugs, then it is down. So somehow we use the name system. We use the term system to mention all of them at once. So in case of failure, if in case of any of these components failed, then the system should be able to recover. And in this case, we say that we have fault tolerance. If one of the components fail, then the system will keep functioning. It should have the resilience to be able to operate again in case of failure. And in this case, we say this system is highly available. So fault tolerant is somehow we are trying to achieve zero downtime. When we say the system is fault tolerant, means we are trying to achieve zero downtime. We can never achieve really zero downtime. Typically, people talk about 5 nines or 6 9 in extreme cases, but this means we are trying to achieve zero downtime. So for example, the airplane is fault tolerant because it has multiple engines. If you want this system to be fault tolerant, we need to look at the components one by one. We need to apply fault tolerance on them one by one. We should have redundant computing engine. Storage, there are many concepts in storage that are mainly to achieve redundancy. If you know RAID, we will discuss RAID later. RAID is a way to store the data into multiple storage medias, and if one of them fail, the data can be recovered from the other medias. The network, we should have redundant component. It should be fault tolerant. For a system to be really fault tolerant, we need to have fault tolerance achieved in all components in the system and also in the logic that connect them together. This seems to be costly because somehow we need to have parallel components. All the components, hardware and software, should have redundant parallel component running all the time and should take over processing if the primary system fail. So how do we achieve fault tolerance in data center? Typically, we need to have redundant systems, not only for the servers and storage, we need to have also redundant power supplies, power system, redundant cooling, redundant IT equipment. We need to have testing. So somehow having redundancy is not enough. Let's say you have 2 generators feeding your data center, and they are connected to your data center in a bus bar, and they have some sort of ATS. We'll talk about them. If you don't test them, if you have redundancy, but you have never tested your redundancy, and you always rely on the primary generator, you have never tested your secondary generator, and in one day, this one failed, and the commercial power failed, and only at that time you discovered that the connection here is somehow faulty, and this generator is running without feeding your data center. Do you have redundancy? Yes, you do have redundancy. You have 2 generators. But guess what? You have never tested your redundancy. You have never run or enabled or tried to test this redundancy in real life. And that's why you have redundancy, but you don't have availability. So you need to have rigorous testing and maintenance for all critical systems to make sure they are ready to operate when needed. And you should have emergency planning, failover strategies. What happens if this one failed, the other one did not take place? You need to measure the failover time between them. You should have maybe some additional backup. Maybe you should have what we call as UPS. We will talk about UPS later. UPS that can cover the time between the failure and the initiation of the other one. So all these should be panic. Panic is one concept. Yeah, panic can help sometimes. Not really. Once you are in panic mode. Now, how to avoid panic? Good question. When there is failure, typically everyone goes to panic mode. And guess what? In panic mode, you cannot think. You cannot think in a systematic way when you are under panic. So how to avoid panic? What do you think, everyone? how to make sure failures will happen. Failures will happen. There is no point. There is no way to avoid them. Failures will happen to any hardware. Any hardware is subject to failure, even if mean time between failures is 100 years. By luck, at certain point, they will fail. So how, yeah, plan. Thank you, Nimaha. I'm sure, am I writing? Yes. So thank you, Nimaha Herring. You should have a plan. And also, you need to test this plan. You need to have some sort of testing. Typically, you have a plan, they do some sort of testing. I know many data centers who run the generator every once a month to make sure they function as needed. So they arrange what they call as maintenance window. During this maintenance window, they try different components, they try the redundancy, the failover, they replicate a failure scenario, they make sure that data center operate as expected in case of a disaster. They run some of the over-the-table tests. They simulate the scenario. They know the role of every person. So you need to do a lot of planning. You need to do a lot of preparation. You need to test this in real life to make sure that, yeah, incident response plan is for cybersecurity. Thank you, Oluwasium. Yeah, for cybersecurity, we always run incident response plan multiple times to make sure that everyone knows exactly what to do during incident. And the same with failure. You must run the scenario to be ready to know exactly what to do to avoid panic. So you need to make sure that even if one component fails, the system keep operating the same way. Proactive, reactive. This is a very nice term, and we will discuss different ways to do maintenance, how to be more proactive rather than being reactive, how to expect the issue before it happens, how to fix the failure before it becomes a downtime. All this will be discussed more in the coming days. Yeah, run some drills for the fire system, drills for all your emergency plans. So this is the way to avoid panic. Now, a question. Which of the following metrics is most crucial for ensuring that a system can handle an increasing workload and maintain optimal performance as the user base grows? What do you think? Most ensuring the system can handle increasing workload. Now, this is a tricky somehow because we did not discuss this concept yet, but let's see. Oh yeah, you got it, all of you. It is scalability. So it is not any of the ones we discussed, it is scalability. Thank you. So now we discussed the meaning of data center, what is data center, and now it is time to discuss maybe the layout, the physical, the structure of the building, different rooms, different spaces in the building, and to be able to familiarize ourselves with the naming and the concepts of data center. So as we discussed, and as I keep repeating, data center is a physical building. And this building has some common layouts that are agreed between all operators. There must be, what rooms you believe must be there? What rooms we must have in data center? What do you think? What rooms and what spaces must be there in data center? UPS room. What is the starting point? The starting point is the server room, right? Thank you, Bertrand. Server room is the core of data center because this is where we have the data, the IT, the servers, the storage. Server room must be there. What else? Cooling. Now, for the cooling, Joshua, do you think the cooling should be inside the same room or outside the room? What do you think? Should we have the cooling inside or outside? Yeah, there should be some components inside to provide the cold air and to absorb the hot air, but this component is not everything. There should be another supporting component that will take the heat and send it outside. So some components of the cooling system will be inside the room, some components will be outside the room. What else? What other components we must have? Let's take the systems one by one. For the IT system, the IT components, do you think most of them will be inside the server room or outside the server room? The IT components. Yeah, most of them will be inside. So the IT components, most of the time will be inside. How about the power components? Do you think power components will be inside or outside? Power components, the generators will be outside, but the power distribution system should go inside. How about the UPS? Do you know what's the UPS? UPS is the device that provide uninterrupted power to the servers. Do you think we need to have the UPS inside the server room or outside? Outside. There is no need. Now, server room is an expensive space. We will have only the components that are crucial, that are essential to run the servers inside that room. Anything else, we will have it outside that room. So for the UPS, there is no need to have it inside. We can just lay cables from the UPS to the distribution system inside the server room. So the power, how about the fire system? Fire system. Now the fire system, some components, the sprinklers should be inside. We will discuss fire system in the next lecture. Maybe the other components will be outside. So as you can see, somehow the server room and the components that are somehow physically related to server room is considered one space. The rest of data center is only for mechanical components, power components that are mainly to support and provide power and cooling to the server room. And we give names to these spaces. We call them gray space and white space. The server room typically is on top of raised floor. Do you know what is a raised floor? Typically, we have the servers, the racks, on top of raised floor. Why is that? Why do you think we have the servers on top of raised floor? So this is the floor, this is the ground. We have some space between the ground and the floor of where we have servers. Why is that? Why do we need to have some space between the actual ground and the floor of the servers? First of all, cooling, ventilation. Yeah, thank you, Stefan. So it is much easier to bring the air from below the rocks, the cold air, and to take the hot air from the top. It makes cooling much easier if we have the servers, if we have some space between the servers and the floor and the ground, and we can use this for airflow. We can use it also for cables. Thank you, Joshua. Cable management, Anipal and Joshua, yeah, we use it for cabling. It makes things much easier if we have some space in the ground. It is much easier than having the cables on cable trays above the rock. It is easier to have it below. And this makes the airflow much better. It makes the cabling much better. So these are the components of data center that we will discuss in more details in this lesson. Let's go over the subjects one by one. So first of all, what is a simple layout of data center could look like? So what are the rooms that must be there in data centers? First of all, we need to have server room where we have the servers. We need to have rack rooms, typically the servers and racks in the same location. We need to have NOC. Okay, now everyone mentioned servers, but how about the team? How about you as data center technicians? Where should you stay? you forgot yourself, everyone. You mentioned the servers, the power, the IT, and we forgot the technicians. So where these technicians should stay? So they should stay in the NOC. Typically, we have certain room where these technicians and operators and experts sit and they monitor the system. So we have some rows where we have the servers and network devices. We have the NOC where we have the operators. We have the power where we connect to the outside power and feed it inside. We have cooling system. Do you think all these systems should be in the same room, in the same physical space exactly? Oh, sorry, Victor, you mentioned this. I did not see that. Sorry. So do you think we have all of them in one room? No. Why is that? Because the servers should have low temperature, maybe 18 Celsius. Oh, how much is Fahrenheit? So I'll mention Celsius. Maybe we can convert it to Fahrenheit later. So the rooms need, the servers need to have low temperature, which means we need to spend a lot of power, a lot of cooling just to bring them to this low temperature. But the NOC, the power systems, the mechanical systems don't need that low temperature. Also, the servers are very sensitive. They are the main assets in the server room in data center. So we need to have them protected. Do you want the HVAC technician to have access to your servers? Do you want the power technician or the electrician to have access to your servers? No, you don't. And that's why we need to have servers in different physical space that is well protected, because these are the main assets we have in data centers. So this is a general view, but this is not really the physical layout. In many cases, the physical layout will look something like this. Give me a minute. Which one? Which monitor? Which monitor? Typically, it will look something like this. Now, this is a typical data center. Question, why do we have two server rooms? Why do we need to have two server rooms? Why don't we have just one of them, one large one, really large one, instead of two medium ones? Thank you. Who said redundancy? Yeah, thank you, Neimaha and Logan. I'm sorry if I pronounce the names in the wrong ways. I'm sorry for that. If you want me to pronounce your name, you can unmute and let me know the name. So yeah, so we need them for redundancy. So in case of any big failure here, we need to make sure that every room has its own cooling system. Every room has its own switchgear power system. Every room has its own generators. Every room has its own even loading dock, and even it has its own water tanks for cooling system. So every room should have its own independent systems. Do you want to have both of them connected to the same cooling system? No? Do you want both of them to have the same set of generators? No. They should be totally independent. If total disaster happen and this room is fully down, all the generators are, whatever happens here, it doesn't affect the other one. This is within the same building. But what about if the whole area is subject to flooding, or maybe earthquake or any other natural disaster? There should be a replica in different geographical location, and we call this georedundancy. Georedundancy means it is not enough to have multiple components in the same geographical location, because if there's any flooding, both components will fail. There is no point. And that's why you need to consider georedundancy by having another data center in another location. Now, do you think georedundancy is more, it is more cost for sure. Do you think every organization will think of georedundancy? Maybe not really. Some of them may feel it is enough to have local redundancy. If you are a small shop, you sell flowers only, and you sell flowers to customers in the same city, in the same area. Do you care about geo redundancy? If there's a flood and the whole area is somehow affected by this flooding, do you think it is a big deal for you to be able to operate even in case of flooding and to absorb the cost of just additional redundancy in another continent? Maybe you don't care because the cost of this geo redundancy is more than the profit you will get in 1 day or 1 week or 1 month. So it depends. But in many cases, geo redundancy is needed. So there are multiple levels of redundancy. We will discuss them in more details in the coming slides. So to be able to build redundancy, we need to have redundancy at every component. You cannot have the best redundancy at one component and then no redundancy at the other. If you have 2 servers and you have 2 power systems and you have 2 switches for network, you have redundancy at all levels. You have 2 cooling systems, and then you have only 1 storage media to store your data. Is this redundancy? Do you have no single point of failure? No, you have single point of failure, which is the storage. And that's why when they build the design, they always emphasize or focus on no single point of failure in any component of the system. And to be able to say I have no single point of failure, you need to understand all the components of the system. To be able to describe your system as redundant, you should have redundancy at all levels of your system. You should have redundancy at all components of your system. So let's try to understand the system in data center. What are the components of our system in data center? First of all, data center is mainly about data. So somehow it is about applications plus data needed for this application. For this application to work, it should have application services, it should have operating system. We call these, what do we call these components? What is the common name for these components? The operating system, the application, the services. What is the common name for these? Software. So software is the starting point. For this software to work, we need to have hardware. We call them sometimes active components. We call them sometimes IT infrastructure. And IT infrastructure is typically 3 components: the servers or the compute, the storage, and the network. So these are the hardware components that are needed to operate the applications. Now for these we call these as IT system. Now, I know that there are cabling and passive components that we did not discuss here, but they are there. There should be cabling connecting these devices. There should be racks and others. Now, for these systems to function, we need to have some physical facility, or sometimes we call them mechanical components, which are the cooling systems and electrical distribution system. Electrical distribution that connects the power from generators to these devices. So there should be some distribution network to connect power. And also we have power coming from the commercial power, from hydro company or from utility company. So the system that connects these is called electrical distribution. And then we need to have a power system with backup from generation. We should have electricity network. And this is the power source. If we want to have redundancy, is it enough to have it in some of these components, or maybe we should have redundancy in all of these components? What do you think? Is it enough to have redundancy in some? No, we should have in all of them. And this is why, as data center technician, you need to understand these components, all of them. You cannot say my data center is 99.999% of availability unless you know that you can achieve this availability in all of these components. And that's why we need to study all of them. We need to know how to measure the availability for each component of these to be able to say with confidence that our system is 99.999% available. Any question about these components, and or maybe do you suggest additional components to these? Security is part of IT. So somehow, now security is somehow to protect the system as a whole. We need to have security, and there are two types and fire system. Thank you. So we need to have security to protect the system as a whole. Security is two types: physical security and cyber security. We need to have fire. Best agree with you. You know that in one data center I worked for in the past, they had issue because the rats were eating the cables, and this caused some systems to fail. So somehow all these protection systems are needed, whether the fire system, the security system, physical, cyber, even pest control, all these are somehow to protect the system as a whole. We cannot measure the availability for these components. They are mainly to protect the system, to make sure that our system is not subject to these attacks or incidents, in addition to the availability. So when we discuss availability or redundancy, we are discussing the intrinsic components, the internal components of the system. But when it comes to external components, this is another thing we will discuss also during this course. Now we discussed the concept of server room and how server room is the fundamental component, maybe fundamental component in data center. So data center is mainly about data, application, and IT, but there are other components to support it. To differentiate between the two systems, the two different spaces in data center, they divide the spaces into two names: white space, gray space. In brief, you can say server room and any component that must be in server room, we call them white space. White space because the raised floor in many cases is white, while the floor in other locations of the data center where we have mechanical systems, the floor is typically gray in the places where we have mechanical systems. So typically the white space is the raised floor room where we have servers, and anything that must be in that room is considered white space component. Any mechanical system that is needed to support the servers, we call it gray space component. So what are the white space and gray space, and what components are in each one? So let's talk about white space. White space is the place where we have the IT equipment, mainly servers. Gray space is any other space where we have back-end infrastructure. So white space include servers for sure, because they are the most protected items in data center. They are typically on raised floor, and we want them always to be cooled, to be protected. So the computing devices, the servers are in the white space. The storage media, the hard disk, the SSD, all where we save digital information is called is in the white space. The network gear, network devices, switches, routers, we will discuss. If you don't understand some of these terms, don't worry, because we will discuss them more in the coming lectures. So where we have network gear is also the white space. We must have the network devices in the same room as servers, because network devices need the same cooling system, the same power redundancy. They must be co-located with servers. The racks, what are the racks? The racks are these things here. You know these large cabinets where we have the servers mounted? Many of these servers, if you go to the center, you will find hundreds of these racks. These are racks or cabinets. We will discuss them also in one of the lectures, but for now, you'll know about them. So racks are mainly in white space. Air conditioning, wow, do we need the whole system to be in the white space? What do you think for air conditioning? Do you think the whole cooling system must be inside the server room? Which component need to be there? Yeah, some component, the component that generate the cold air and absorb the heat, the hot air, should be in the server room because it is there to control the environment of server room. But this unit should be connected to chillers and other components that will be in the gray area. So the air conditioning unit, some components are in the same room in the white space, other components are in the gray space. The same with power distribution. The racks and the servers should be powered, which means there's some components of the power system that are used to connect the power distribution unit, PDUs we call them. So the power distribution unit, the power distribution system must be in the same server room, white space. The rest of the power system, the switchgear, generators, UPS, is all in the gray space. So what will be in the gray space on the other side? The switchgear, electrical equipment that control the ATS and other components, we will discuss them in more details later. They are in the gray space. The UPS, we don't need to have the UPS inside the server room. It can be outside. And also, we don't want the technicians who serve and maintain the switchgear or the UPS or the transformers to enter the server room. Servers are critical components. They hold confidential information. We don't want anyone to have physical access to them unless needed. So the UPS is gray. We will talk about UPS later. UPS is a device that provides power to the system in case of power failure, and they work momentarily, immediately. They don't need any time to initiate like generators. Transformers are mainly to transform or change the level of AC power. When the AC power is transformed between or transmitted between cities, it is transmitted at high power levels, 11K or maybe more than 11K kilovolt. This is mainly to reduce the loss of power. But when you enter the building, you need to step down the power level to be 110. It goes through multiple stages, but in all cases, transformers that change the level of AC power are considered gray space. The chillers, which are part of the cooling system, part of the HVAC or cooling system, they are in the gray space. They don't need to be in the same room as servers. Generators, for sure, are gray space or even outside in many cases. So these are the differentiators of white space and gray space. Which area is more secure? Which area is more restricted? The white space or gray space? The white space is more restricted. Only data center technicians, only consultants, only maybe IT staff are allowed to enter the white space. The security measures are different in white space than gray space. Gray space, in many cases, open to contractors, to servicemen, to maybe also internet providers, ISPs. They may enter some areas of the gray space. Sorry. Any question about white space and gray space? We will talk about safety training, Logan, somehow. Okay, before I start the questions, let's talk about here, this. So in this area, the white space is only this and this. The rest is gray space. Now, a lot of people ask, how about the offices? Are they white or gray? I couldn't find any clear definition. Some people say if the offices are inside the server room, they considered white space. Sometimes the server room is not a good place to stay in because it is cold, it is noisy, but in some cases you may have one or two offices inside, maybe to do staging. So if you have offices inside server room, they are considered white space. If they are outside, maybe they are gray space. But typically no one sit 24/7 inside the room. Sometimes you have some staging, some place where you maybe connect the devices, maybe, or maybe you want to configure something by console. So this is somehow part of the white space. Anything outside is gray space. Why they call them white and gray? I believe white is mainly because the raised floor is white in most cases. And in other areas, they have cement. They have the ground cement only, and that's why it is gray. I believe this is the reason why they call it. The term started in the US. People in the US like to have simple terms. They don't like scientific, complex terms to describe things. They want to describe them in an easy way. And that's why I believe they just use the colors. They said this room is typically white because the ground, the raised floor is white. So let's just call it white space. The rest of the data center is gray because the main color there is gray, and that's why it is just gray space. And then these terms became some sort of standard. When they build the security, the physical security rules, they have physical security rules for white space and physical security rules for gray space. Yeah, we will talk about raised floors later. So question, what infrastructure is typically found in the gray space? Select all that apply. What do you think? A, B, C, D. Don't read here. You can select more than one, by the way. Actually, it is only one. Now, cooling equipment is some sort of tricky because cooling equipment can be here or there. So some units and the cooling equipment are actually, we will discuss the concept of this term later, but some of them inside, some of them outside. So gray space, for sure, the even power distribution. Yeah, so the cooling equipment is considered. Actually, it is C. Power distribution, they mean even the power distribution needed inside the server room. So this is somehow tricky, but it is cooling equipment. I agree with you. Elements of A can be outside because power distribution start from the gray area, they enter the white area. But yeah, if you need to select only one, maybe it is cooling equipment. Now let's take another example to understand gray space and white space in a better way. Let's take another external sources. When I use external resources, it is just the first resource I find in Google. It doesn't mean I give any endorsement for this website or any endorsement for the information. It is just for me to explain the idea from different angle. So white space typically includes server storage, network gear, network devices, the racks, some of the air conditioning units, and the power distribution system. Gray space, the switch gear, the electrical system, the UPS, transformer, chillers, generators. They have some drawings here, no, not here. The other one has drawings. So white space is typically for the servers, gray space, anything else. The operators are typically outside. So this is some sort of neutral area maybe, because they are not equipment, they are humans. So, but anyway, this is something you can consider. So the white space, server storage, network equipment, rack, power system, some of the air conditioning units. So air conditioning units, the ones that generate cold air, are inside the white space. The chillers, which are the back-end system for the cooling system, are outside. We will discuss the cooling system later. These terms will be clear later once we discuss this in more details. This is a typical layout. We have the server rooms. So this is a typical layout for data centers. Server room is the main component. We have some generators outside. We have some heat exchange. Now the cooling system include components here that generate cold air. These components are connected to chillers. We use water typically to transfer heat from the room to chillers. The chillers is the central unit. They have another loop. So we have loop to collect the heat from the server room, another loop to send the heat to external unit. This external unit will dissipate the heat. So somehow it is all about heat exchange. We want to take the heat from here to there. We have a unit here to absorb the heat and send cold air inside this room. The heat that is absorbed from here is transferred through one loop here to the chillers. The chillers will take the heat, send it to another loop. These loops are totally independent for different reasons. We don't want to have one loop. Then they will take the heat, send it to another unit. This unit is responsible to dissipate the heat into the outside ambient environment. And this way we take the heat from here to there. We should have some room for the NOC operators. We should have some rooms for the physical security. So the layouts will be different from one location to another, but in most cases, they must have the same number or same components to serve any data center. Now, raise the floor. Why do we need raise the floor? As you discussed before, raise the floor is mainly for heat to make the airflow better, to improve airflow. Why do we need airflow? Because remember, we want to keep the servers cold, and this means we need to have a way to take the heat out of the servers, send it to the outside. We will discuss this cooling system later in more details. So let's watch this video about the data center, about the raise the floor. Did I share with, let me make sure I share with sound. Oh yeah, I shared with sound. So let me make sure I'm sharing the right screen. Let's watch this video and discuss it after the video. There is no sound in this video, by the way. So this is the room, this is the ground, but we cannot have this. By the way, there are certain cases where we can have the servers on the ground without raise the floor. In this case, we need to find another way for airflow and another way to lay the cables. But raise the floors are common. So raise the floor, they use some sort of mesh to install the tiles on top of them. Then we have the power system and different systems on the sides. This is the main circuit breaker. The main function of raise the floor to make the air flow freely from the cooling unit, the crack unit, and circulate it, collect the heat or the hot air that we will discuss later in more details. Then we have it. we should have two power supplies. One of them is the brown one here. We should have two power sources. So maybe one of them come from certain utility company. So this is the first power source. Every cabinet, every rack should have two power outlets, two power distribution units. So there is one power coming from the green side, one power coming from the brown side, and both of them connects to the rack. So the rack has two power supplies, one coming from the brown power supply, one coming from the green, and every component inside the rack should be connected to both of them. Even if the component has four power supplies, two of them connected to the brown, two of them connected to the green. So it is much easier, much cleaner when we have raised floor. Everything is hidden below the raised floor, and our data center looks clean. The airflow is much better than if we have our servers on the ground. We will have a lot of these rows. And here we go. Does it make sense? Do you like the idea of raised floor? Now, raised floor is not the only way. We will discuss other concepts later, but I would say I don't have percentage, maybe 80%, maybe 90% of the cases, data center will have raised floor. Now, cabling is another component that we must have. We will discuss cabling in much more details later, but cabling typically have two components. We have the cabling, horizontal cabling that connects the cabinets or the components to one central point, and we have vertical cabling. In vertical cabling, we use fiber most of the time. In horizontal cabling, we use UTP most of the time. Now, we will discuss UTP and fiber in more details later, but for now, just to let you know that structured cabling is one of the important components in data center, and that's why we need to design it in a proper way. Typically, do you know what we call the room here? The point or the area where we connect the building to the outside world. Do you know what we call it? What is the typical name we give to this room or area? The mark, yes, sometimes, or we call it MDF, main distribution frame. And then we have the IDF, intermediate distribution frame. We will discuss these in more details. Whatever we discuss today will be discussed in much more details later in future lectures. So this lecture is somehow an overview. No spaghetti, we will talk about this later. Now, redundancy. What is redundancy? Redundancy means we need to have extra components available in case of failure. So if I have a device, if I have a server, and this server needs two power supplies to operate. To operate, it needs two power supply. It needs maybe 2000 watt, and every power supply provide 1000 watt. So for this server to operate, we need to have two power supplies. 2 is N. For this server to operate, it needs at minimum two power supplies. I have two power supplies. Is this redundancy now? Is this redundancy? It is MDF, Stephen. Sorry, Stephen, for your question, it is MDF. We will discuss MDF later, main distribution frame. So let's go back to the N. So with two devices, with two power supplies, is this redundancy? I have two power supplies, which are the minimum to run the server. No, I have no redundancy because I'm running only the minimum. So although I have two components, this is not redundancy because both of them are needed to operate the system. If one of them fail, do you think the server will run? If one of them fails, no, the server will fail. So N is the minimum. So this is our starting point. N is the minimum. If I want to have redundancy, I must add another component. What do we call this setup with one additional component? We call it N plus 1, which means I need to have two power supplies at minimum to run the server. So my N is 2. If I want to have redundancy, the minimum redundancy is N plus 1, which means 3 power supplies. Now, if this server needs 4,000 watt and every power supply can provide only 1,000, how many power supplies at minimum I need to run this server? I need 4. In this case, what is in? In this server where I need 4,000, what is in? In is 4. So the minimum is 4. If I want to have redundancy, I need to add 5th. Minimum redundancy is 5th. If I have 5, I have n plus 1. Is this enough? Is it enough to have only one additional component? Not really. It is good. We have redundancy, but in many cases, this is not enough. We have different levels of redundancy. At minimum, we need to have n plus 1 at minimum. But in many cases, we need to have 2n. We need to have double. So if my server needs 3, if my server needs 4, if my server needs 4,000, and every power supply can provide 1,000 only, if I want to have good level of redundancy, if I want to have fully mirrored, maybe I should have 2n. I should have 4 power supplies to run the system, and then another 4 power supplies with their connectors, with everything fully backup, fully mirrored. So I have 2 different power supply systems to feed the server. Each of them is 4. This is fully mirrored. But if I have n plus 1, this is the minimum. I can survive with single failure, but this is not a good level of redundancy in many cases. If you want to achieve 5 nines, there's a good chance that we need to mirror all the systems to be totally independent. So I have the system totally mirrored in 2 different locations to consider my system really redundant. And not even this only. In some cases, if your data center needs 3 generators to operate, so you have one system with 3 generators, another system with 3 generators. If you want to have, in some scenarios, you may need even 2n plus 1, which means on top of that, you have 1 backup generator. In addition to your full replication, you have 1 backup generator just in case. So you can go the minimum, n plus 1, fully mirrored 2n, or fully redundant power 2n plus 1, which is the suggested in many cases to achieve 5 nines. Now, you may find data centers with 2n, you may find some systems with n plus 1. Sorry, but we are aiming for this level. And during the course, we will discuss how to achieve this in all systems we have in our data center.